Alright, in this video I'm going to go over confidence intervals specifically for independent and dependent t-tests, but I'm also going to review one sample confidence intervals so you can see the connection between them and see that there's just a basic formula for all confidence intervals for t-tests. So, as a review, a confidence interval is an estimate of the true population parameter. The parameter can be a mean or it can be a proportion, but we're going to focus on means in this class. And it could be the difference in means or different scores, the mean of different scores, whatever you're talking about. And we give a range of values, so we create a lower and upper bound, and we say it's likely that our population parameter is between those two values. So the smaller the width of the confidence interval, the more precision we have, and the more informative the confidence interval is, given that we have a high confidence level. So for example, if I say that this class's scores are between 0 and 100 percentage points more than my previous classes, that's not very informative at all. It could mean that, there's no difference between your average scores if I got a 0 difference, or it can mean you did like 200% better than them. We got 100%. But if I said, okay, you're between 10 and 50 percentage points. On average, you do better 10 to 50 percentage points better than my previous classes. Well, at least now you're like, okay, now we kind of know that we did better. How much more? 2% is pretty good. But 50 would be like a lot better, right? It's not very precise. It's still kind of a large range. But if I said you guys did better, and more specifically I said with say 95% confidence that you guys did between 9% and 11% better than my previous classes. And that's pretty precise. 9 to 11 percentage points isn't a large range, right? A range of 3 percentage points isn't that big, and the difference between 9 and 11% is not a big deal. So if we have a 9 to 11% confidence interval, so the lower bound is 9%, the upper bound is 11%, then we have a pretty precise confidence interval. So the smaller, the more precise, and generally the more informative. Unless you have a really low confidence level, then that's not informative at all. We'll go over what that means a little later on, but as long as you have a good confidence interval level and you have a precise confidence interval, then you have more precision and it's more informative. So I'll go over some examples. So one sample example is with 95% confidence, I estimate that women weigh between 150 to 170 pounds. So in this example, we only had one sample, and that was the average, and we got the average weight of the women in our sample, and we calculated a confidence interval. Our lower bound was 150 and our upper bound was 170. We could do an independent two sample example. So we could say with 90% confidence, I estimate that men weigh on average 20 to 30 more pounds than women. So now we're comparing two samples, the average of men and the average of women. But we still have a lower and upper bound, but now we're calculating the confidence interval on the difference between the sample means instead of just one sample mean. And then a dependent example would be with 99% confidence, I estimate on average a person's pre-score is 10 to 20 points lower than their post-score. We're still comparing kind of two things here, But now, in this example, we had a repeated measure design, meaning the same person took the test twice. And so now we're comparing within person. So we're saying, on average, this person's score was higher on the post-test than the pre-test. So we're not comparing two separate samples, we're comparing within a person. It could be within other pairings like twins, but a lot of times it's within person. So you can see how I worded the independent versus dependent example a little differently. The confidence levels were not random, well, kind of random, but these are common confidence intervals and confidence levels, and I didn't pick them depending on what kind of tests we're doing. You pick that regardless of what test you're doing. The most common one is 95%. Here's our basic formula. So we have our sample statistic that will, of course, change depending on what kind of confidence interval you're doing. And so, it's usually a mean, some kind of mean or a difference of means. And then plus or minus your margin of error. So remember, our sample statistic or the mean is an estimate of the population mean, or the difference of the population means, plus or minus some margin of error. So we're not 100% sure, so we kind of make a range of values, and that margin of error helps us make the range of values. And the margin of error is your t critical times the standard error. The lower bound is your sample statistic, a lot of times the mean or the difference of mean, minus the margin of error. And the upper bound is your sample statistic, which is the sample mean or difference of means, plus the margin of error. The t critical in your margin of error is determined by the degrees of freedom and the confidence level. The higher the degrees of freedom, the lower your t critical is. And then the higher the confidence level, the higher the t critical is. The confidence level, some common confidence levels, as I said before, were 90, 95, and 99%. The most common is 95%. A 90% confidence level, for example, means that in the long run, 90% of confidence intervals will contain the true population parameter, usually the mean or the difference of mean, if you have random selection. So the confidence level is talking about the long run. In the long run, how many of these confidence level intervals will contain the actual population mean or the difference in means. A single confidence interval has a true population or not, and we're really not sure if it has it or not. So it's just likely that your single confidence interval has a true population mean or difference in means, but it's not guaranteed, because you could be that unlucky person who doesn't get it. So if you have a 90% confidence level, and that means 10% of the time that a confidence interval doesn't have the true population mean or difference of means. So the higher the confidence level, the more sure you can be that your confidence interval contains the true population mean. So it still might not. You could still be that unlucky person and get one of those confidence intervals that doesn't have the true population mean. So if you had 99% confidence level, that means 99% of the confidence intervals will contain the true population mean or difference in means, and 1% of the time it will not. And you don't know if you're the 99% or the 1%. You could have just got really unlucky and got the 1%. So having just one confidence interval is very helpful, but don't always depend on just one. You want to look at other research people do, not just yours, and see if they get a similar answer. And hopefully the more the better. Okay? So on this slide, we're going to talk about how to get more precision. So remember, precision means you have a smaller confidence interval. And generally, more precision is good unless you have a low confidence level. And there's 3 ways to get more precision, and the last way is bad because you're affecting the confidence level. So 1, you can have higher sample size. So that means you have higher degrees of freedom, which means you're lower the T critical is, and then that means you have a lower margin of error and thus a lower or a smaller confidence interval. But also because you have a higher sample size, it means your standard error is going to be smaller. So if you have sample means that are based on higher sample sizes, then that means you're going to have smaller variability between the sample means. So you're going to have a smaller standard error. So remember the formula for one sample test for the standard error is the standard deviation divided by the square root of n. So if you have a higher sample size, so you have a higher number in the denominator and you divide that, you're going to get a smaller standard error. So increase your sample size, right? Without thinking about the formula, that's kind of intuitive. If you have a higher sample size, you're going to be more sure of your confidence interval, right? If I estimate a confidence interval on 5 people, you're not going to be too sure, and you're probably going to have like a wide range even if you didn't formally calculate the confidence interval, right? But if you have 1,000,000 people, you're going to be like, okay, it's probably around this value, even if it's not exact. Okay, so it's just intuitive. The higher the sample size, the more precise you can be, the more sure you are. The second thing you can do is have a smaller standard deviation. So the smaller the standard deviation, the smaller standard error. Because remember, the standard error is the standard deviation divided by the square root of n if you have a one sample test. And so if you have a smaller standard error, you're going to have a smaller margin of error, and thus a smaller confidence interval. So notice what we're doing is we're lowering the margin of error, and that means we have a smaller confidence interval. So how you can have a smaller deviation is you can either have just a more precise outcome variable. So you're just measuring it more precisely. So I think I had the example before, if you're measuring height in just feet, so you say people are either like 4, 5, or 6, maybe 7 or 3, but not as many. But if you just measure them in feet and don't get their inches above that foot, then you're not going to have a very precise estimate. And so your estimate's going to be, your margin of error is going to be really high. But if you get really exact and you have the feet and inches, then you can get more precise. You can say, the average person is, for example, the average woman is between 5'3" and 5'5". But if you just measure people's feet, then you're going to say it's between 5 and 6 feet, right? Because you don't know how many inches they were. But you know that it's between 5 and 6 feet, but you can't get very precise because you never measured the inches. But if you measured the inches, then you can get more precise. So just be more precise in your outcome variable, then you're going to have a smaller standard deviation, and that's going to end up making your confidence interval smaller. And then number 3, you can have a lower confidence level, which means you have a lower critical T, a smaller margin of error, and a smaller confidence interval. But this is a bad idea, because if you have, for example, 20% confidence, then that means only 20% of the time your confidence interval is going to contain the true population mean or difference of means. So you're only going to be kind of right 20% of the time in the long run. So you can be right less times than you're going to be right less times than you're wrong. So you're going to be wrong more than you're right, and that makes no sense. So don't go lower than 90%, or that's kind of consider it a little bit big anyway. Usually it's 95%. Now, why we pick 95 and not 96 is kind of arbitrary, but we have a high confidence level because that means you can be more sure of it. You don't want to go too low because then you're just guessing. You might as well just guess if you have a 20% confidence level. Or you might as well just say it's your sample mean because it's really not going to be very informative. So the basic formula is that the confidence interval is your sample statistic plus or minus the margin of error, and the margin of error is your t critical times your standard error. So here's a chart of the different tests and what the sample statistic is that I'm referring to for t-test. So for one sample mean t-test, the corresponding sample statistic is just the sample mean. So you just have one sample, so you have your sample mean. Independent t-test means you have two separate samples, and so you have two separate sample means, so it's the difference between them. It's the sample mean from the first one minus the second one. You can switch it depending on how you want to do it, but it's still the difference. And then for the dependent t-test, it is the sample mean of different scores. So in this case, the dependent t-test, we create the different scores based on the pairing, and then you get an average of those different scores. But with the independent t-test, you have one for each column. So you have the mean of the first sample minus the mean of the second sample. So that's a little bit different. And then the critical t's are found by getting the degrees of freedom. And we can use Excel to get the critical t's. You can use the t.inv.2t test, or function, sorry. And what you enter is the alpha level, which they call it probability in Excel, and then enter the degrees of freedom. So to get that kind of alpha level, it depends on your confidence level. So you take 90% and then you transform it to a proportion, so that's 0.90. And then you do 1 minus 0.90, and that gives you 0.10, and that's what you're going to put in Excel. If you have 95%, then you're going to change that to 0.95 and do 1 minus 0.95, and then you get 0.05. And then if you have a 99% confidence level, you're going to change that to 0.99 and then do 1 minus 0.99 and you get 0.01. So that's what you'd put in the probability part on the function in Excel. Then to get the degrees of freedom, it depends on the type of test. So if you have a one sample mean test, you just do the sample size n minus 1. If you have an independent t-test, you do the degrees of freedom total. And you can get that two ways. You can find the degrees of freedom for each sample, which is the sample size minus 1. And you do that for each sample, and then you add them together. Or you can do the sample size for the first sample plus the sample size for the second sample minus 2. Either way, it gives you the same thing. You just want to use the degrees of freedom total. And then for the dependent t-test, it's the number of pairs minus 1. So ND, so the number of different scores, is also the number of pairs. And then you just subtract 1. Standard error also depends on the type of test. So if you're doing a one sample mean test, then it's the standard deviation divided by the square root of n. For the independent t-test, it's the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. For the dependent t-test, it's very similar to the one sample mean test, but we're talking about different scores. So we have the standard deviation of different scores divided by the square root of number of pairs. And for the independent t-test, we're assuming that the two population standard deviations are equal. If you don't want to assume that, you'd have to use another formula and different degrees of freedom, and I don't go over that in this class. but that's just a note about it. Alright, and then finally we put this all together. Here's how you do the confidence interval. So we have the sample statistic plus or minus the critical value times the standard error. So you put it all together. Here it is, but remember it still takes on that basic formula. It's just the basic formula is a little different because we have different components for each of the parts of that formula. If you want to get more examples of how to, do it, that's just overviewed it. I didn't really do a specific example. Then go to the PDFs that I have posted, or I'll go over an example in another video where I go through. I'll have another video for the independent test, and I'll go through a hypothesis test and a confidence interval and a Cohen's d for the independent, and then I'll have another video for the dependent. I'll go through all the same things, but I just want to do it all together instead of splitting it up. But this just goes over, it just has an overview of it.